Okay, so today we're going to finish up these last of the fluid mechanics stuff. And we've got kind of two big equations left. And they're related to each other. So this is the one we talked about yesterday with the syringe. So, and that's typically how this plays out, or like you put your thumb over the end of a fire hydrant, something like that. But here's the main idea of this equation, is that if you look at the units, so that's meters squared times meters per second, which is cubic meters per second. So what this is a flow rate, okay? So because this is a flow rate, then basically what we're saying is that if I take this syringe, and I can either have the back of the syringe moving slow and moving a big area of water, which is going to be the same as a very small area of water moving really, really fast, okay? Now, here's kind of where the magic happens with this. If you're comparing two circular points, okay? So that area of this one is going to be pi times, so let's say, for example, this is going to be, we'll make it easy. Let's say it's 2 centimeters, which would be 0.02 meters squared. And let's say that that's moving at 5 meters per second. So then, let's say this is 2 centimeters. So let's say the area, this radius here is, say that's 2 millimeters, okay? Well, 2 millimeters is going to be 0.002 meters squared times pi. And let's say we want to figure out what that new velocity is going to be, okay? So we want to figure out how fast that's going to be moving out. Well, conveniently, if you look at this, as long as it's a circle, you even have to worry about the pi calculation. Because if you set it up, that's just going to be that squared, okay?
Mr. Burkin.
What?
Can we back up? Can you explain what that P1 plus PGY plus 1/2?
I'll get to that. That's the continuity equation. I'll get to that.
Oh, okay.
No,
I thought you derived that from AV.
No. They're related, but I'll show you. Well, I'll get to this equation in a second. Okay. Cool. Don't worry about that for now. Okay. So here's the point. These pi's are going to cancel out, right? So if you look at this, so somebody take 0.02 and square that.
0.004, right? 0.004?
0.004 meters squared times 5 meters per second.
I've already seen these zeros.
Okay. Now, if you take 0.000 with 0.002 and square that, what do you get?
0.00008.
A lot of zeros.
8.
This is why you have calculators. I wanted a scientific notation anyway.
You got one too many zeros on that 0.00.
Well, you have on the first one,
Yeah,
too many. Or no?
No, because 0.02 squared is 4 times 10 to the negative 4.
Whoa.
4 times 10 to the negative what?
4.
Oh, never mind.
Which is right.
That doesn't feel right.
0.002
I
squared
don't
is
Well,
4 times 10
So
to the
4
negative
times 10 to the negative fourth, right?
Yeah.
Meters squared times 5 meters per second. And I don't want that number. I'm just going to leave that out there, okay? And then 0.002 squared to get you what?
4 times
10 to
10.
the negative 6.
4.0 times 10 to the negative sixth times some velocity.
Where
Now,
did we get pi from?
Is the area
because it's the
of a circle.
cross-sectional area of a circle.
Oh, we're doing, okay.
But I got pi's on both sides.
Yeah.
So somebody take 4.0 times 10 to the negative fourth and divide that by 4.0 times 10 to the negative sixth.
100.
What?
100?
Yeah.
100, right?
The fours cancel out, and then it's
Okay?
come on, man.
So notice that this
You
becomes
get 10 to the second.
500, right? So, which is faster than the speed of sound. Pretty cool. So here's the point. If you just look at this in terms of a ratio, so if you take 0.02, so somebody just do this. Somebody take 0.02 and divide that by 0.002. What do you get? 10, right?
25.
But that's a ratio that's going to get squared.
So it's 100.
100.
Oh.
10 squared is 100. So if I take 100 times 5, I get 500. So if it is, because it's squared, and this only works if it's two circular objects, okay, where I've got this coming out of a smaller circle here. It's going to be a ratio of the radii squared, okay? So that can save you a lot of math. You say, oh, okay, right, it's just a ratio of the radius squared because of the fact that your flow rate has to stay the same. Now, here's the bigger idea. Beyond just the little mathematical tricks, the bigger conceptual idea is that whatever volume of water is moving through this part has to equal the same volume of water that's coming out. Because what we're assuming is that this fluid is not compressible, okay? So the main thing I want you to get that's going to lead into the next equation is that when you reduce the cross-sectional area, what has to happen to the velocity? It has to go up, okay? That's the main idea. Just hold on to that thought. Now, then you have what's known as Bernoulli's continuity equation. So I'm going to write this whole thing out. And it's some jacked up units. Now, if you're gonna, what do you know, if you're gonna add numbers together, what do you know about the units?
Have to.
They have to be the same, right? I can't take kilograms and add them to meters. So as jacked up as this unit, or as this equation looks, it only works if we can add things together. If we can't add things together, we're dead in the water. So let's start with P1, okay? So that's gonna be some initial pressure. So that's going to be in what? Newtons per square meter. It's pressure, right? Now, this is going to be rho g y1. So here's what I want you to see in terms of this equation. You have a pressure part here, okay? That's that. So this is rho g y. So this will make sense in just a second. This is like the gravitational potential part of it, because it's, if you look at rho g y1 and rho g y2, what we're going to look at is like what happens when you take water that's underground in a big pipe, and then we're going to restrict that down to a water fountain, where that water fountain has a much smaller diameter, but it's going to be going faster. So this part here is basically an UG part. It's a gravitational pressure part because it's rho g and then you have a height, okay? Now, the rho g v1 squared, that's like the kinetic energy part of it. So this is how fast that fluid is moving, okay? So, if you look at the units, so this rho is going to be in kilograms per cubic meter, times g, which is going to be meters per second squared, times h, which is going to be in meters. So if you look at what happens, right, so we can cancel out one of those. That leaves us kilograms meters per second squared, otherwise known as newtons, divided by meters squared, exact same thing. Okay? So both of these are newtons per square meter. Looks completely different, but at the end of the day, that's what you end up with. Now, then you have 1/2 rho v1 squared. Well, rho is still going to be per cubic meter. But now you're multiplying it by V squared, which gets you
Meter squared per
meter
second
squared over
second squared.
second squared. So again,
Newtons per meter squared.
I can cancel out,
1
and I get,
kg meter squared.
I only canceled out one of those. I don't want to cancel out all of them. So then I get kilograms meters per second squared over meter squared, which is the exact same thing as meters per square meter. So that density, which is not to be confused with buoyant force, that density is the density of the fluid itself. Typically this plays out with water. Okay, so a lot of times what you see, this is like flow rates with water. Oh, okay, right. That's a certain amount of volume. It's water. It's not compressible. Okay, it isn't like air where you could, don't run air through your, or water through your air compressor. It's not going to work well because you can't compress water.
Why not?
Basically because there's no give to it. There's no empty space between it to compress it. Okay, that's why.
It's already too tight.
All right, so here's how this plays out. Typically what happens is this is how your water distribution system works. A lot of times you're going to start off, you're going to have like a big water tower. You're going to have water stored up there. Okay, so what's the purpose of having that water stored in a water tower?
Gravitational potential.
Yeah, you're storing gravitational potential energy. Okay, so you've got to do work to lift the water up there. Okay, then it's going to come down. It's going to come into like a bigger distribution pipe. Okay, so underneath the ground, you might have a pipe that maybe has a diameter of 20 centimeters. Okay, which would be about like yay, right? Now, but when what you drink out of isn't a pipe that's this big, it's like the awkward, okay? You drink out of a little, much smaller area. But, so here's the ground level, right? So, when it comes up out of the ground, there's a couple of things that are going to happen. Number one, we're going to narrow that down, okay? So, if you look at this equation, P1 plus 1/2, or hold on, rho G Y1 plus 1/2 rho V1 squared equals P2 plus rho G Y2 plus 1/2 rho V2 squared. Okay? Now, if you're clever, and you all are, what are you going to let the value of y1 equal?
1.
0. You're just going to call that 0. We're just going to call that our baseline. Okay? So we're going to let that be 0. So here's going to be the significance of this. This is going to be 0. This is going to be how much pressure there is in that pipe. Okay? This is going to be some pressure. This is going to be this velocity. Now, here's what I want you to see. This is this big pipe down below the ground, right? It's going to go up, and we're going to constrict it down. So this is where this A1 V1 equals A2 V2 ties in with this equation, okay? So down here, you have a big cross-sectional area down below the ground. As it comes out, you're going to have a smaller cross-sectional area. So what has to happen to that velocity?
Increase.
It has to increase. So here's what I want you to see. So this is the velocity that's in the pipe below the ground. So this is because it has a bigger area, this 1/2 rho, that's going to be a fairly small velocity. So the water underneath the ground isn't moving very fast, but you got a big cross-sectional area. So that's like this part of the syringe. Okay, so imagine this is down below the ground. And then we're going to hook up a hose, it's going to come out here, right? Now, I'm going to leave out P2 for just a second, okay? The rho G Y1, we're going to set that as 0, that goes away. This is 0, okay, plus P1. Now, I'm going to leave P2 out of this for just a second, okay? Don't worry about that. Leave 2P out. I'm going to leave P2 out. So what's going to happen over here is that now this, because it's above the ground, now we're going to have now we're going to build potential energy because we're lifting this water up above the ground. Okay, we're lifting it up. So this is going to be some positive number, right? Because now that we're storing potential energy, because we're going from below the ground and up. So this is going to be some positive number. Now, then we're going to have 1/2 rho v2 squared. So what do you know about this velocity here on this compared to the velocity coming out of the pipe versus the velocity down below?
This will be bigger.
Faster. Why?
Because it is smaller.
Because you've constricted that. It's like you're holding your thumb over the end of the hose, right? So this is going to be a big positive number as well. Now, don't discount the importance of this equal sign here, okay? So here's what I want you to look at. These two, mathematically, all these both sides have to add up to the same thing, right? So you're storing potential energy because you're lifting this water up. It's moving fast, so you have a big kinetic energy part. So what do you have to do with this pressure to balance it out?
Negative.
Well, you can't have negative,
Small.
but it has to be small, right? So what happens is that the pressure under the ground is really big, okay?
Yeah.
But then when it comes out of the ground, you equalize it by lowering the pressure. So basically, you're going to take that big pressure moving underneath the ground. So if you've ever seen like the effects of what happens when a water main breaks, water goes flying everywhere. Okay, it's like a geyser because it's under so much pressure. So on the bottom side, you have a high pressure with water moving slow. When it comes out of the ground, you have a lower pressure system, but the water is moving faster.
How does that work?
What do you mean?
Like, how do you have low pressure, how do you have really high pressure, but it moves slow?
You're just like
It's a big
this.
area.
Okay, your difference is the area because you've got these big, massive water mains underneath the ground. So it's carrying that same volume of water as coming out of your faucet.
Yeah.
Okay,
But how does the faucet have less pressure? Because doesn't it like condense and then speed up? So the pressure is.
funny you should ask. I have two pieces of paper. Okay, and this is the next part of the equation.
Oh.
Okay.
Really? Here's the work.
So I'm going to have these pieces of paper, and I'm going to blow down between them. Okay? So I'm going to blow between the sheets. Okay? So 3 things could happen. What are the 3 things that could happen when I blow between those sheets?
They wiggle.
Could explode.
Well, okay, they could explode. Okay? They could either move
Outward.
out,
Inward.
they could move in,
Or
or they
stay the
could
same.
just not move at all. Okay? That's it. So
Definitely gonna move.
I'm gonna hold them like this, okay? And I'm gonna blow quickly in between them. So they're gonna move. They can move out because I'm forcing that air in between them. Okay. They could just stay still because the fact that air pressure is still pushing on both sides and it's still going to be equal and nothing's going to change. Okay. Or because the air is moving so fast, it creates like a vacuum and they get pushed together. So those are your 3 options. They move out, they just stay the same, or they move closer together.
Move out.
So how many vote that the pieces of paper are going to move out?
I do.
Okay? How about they just stay the same?
I didn't like his explanation for moving in.
You're on the same train.
Yeah.
Nothing's going to happen. How about they move closer together? Nobody's on that train.
Nobody's
Okay.
on a lot of trains.
I'll be on both
You ready?
trains.
Here we go.
Dang it.
That's cap.
Should have known.
You do it then, Louis.
He's cheating.
I'm cheating.
There's a magnetic papers whenever you blow air through them.
Yeah,
That's not even
you're
work,
activating
bro.
the magnet.
I'll move closer.
Oh.
Why?
Oh, they like each other.
Oh, low pressure,
Oh, no,
high
no, no,
pressure.
no. Start with the basic idea. Start with this basic idea. When I blew through them, did the papers accelerate?
Yes.
Yes. So what does that require?
Force.
An imbalanced force, right?
Yeah.
So right now, if I just hold this thing up, is there pressure? Is there air pressure on this side of the paper?
Yes.
Is there air pressure on this side of the paper?
Yes.
Two sides of the paper have
Same air
Equal pressure.
equal pressure because you have the same number of collisions on both sides, right? Right? Now, when I blow between the two, okay, I'm directing that flow down here. So what's happening to the number of collisions on the outside? So imagine I'm blowing on this side. So what's happening to the collisions on the outside of the paper?
They say the same.
They're going to stay the same. Okay? I'm not going to change the number of collisions on the outside of the paper. But what's going to happen to the number of collisions bouncing this way on the inside of the paper?
Decrease.
They're going to become
Small. Less.
smaller. Because that air is being forced down this way. So I'm going to have the same number of collisions on the outside with the smaller number of collisions on the
inside.
Therefore, you have an imbalance of forces, of pressure. What's going to happen? They're going to get pushed together.
Pop would be like, I don't like that.
Okay?
Pop would say, I don't like
I
that.
was going to go, yeah.
I don't-
So do
I don't
this,
believe it.
right? So they're far apart.
Oh, yeah.
Okay? They get pushed together because I'm creating a low pressure system. So back to your question.
Yeah.
Okay, if you apply this to water, right? So what's happening then in terms of pressure, you have a high pressure because of the fact that if you look at this in terms of like collisions.
Yeah.
So you have that pressure, that water down below that's moving slow. So when I move that air, it's just like this. When I move that air faster, I create a system of low pressure because it's moving faster. So that's why when that water comes out, it's under a lower pressure than it is in that big pipe down below. Now, hold the thought, hold the thought. Look at at a wing on an airplane. Because somebody brought up laminar flow the other day.
Oh, me.
Okay, so here's a cross section of an airplane wing, right? What's the function of an airplane wing?
Decrease drag.
Well, fundamentally,
Well,
it's
increase
designed
lift.
to do what?
Keep it in the air.
Create lift. Okay, that's what airplane wings do. Airplane wings that don't create lift don't work so well. Okay, they don't really get off the ground. So the air comes in, right? Air comes in, and part of it has to come up over the top like this. Okay? Stuff on the bottom pretty much just goes straight across. Now, because of what's known as laminar flow, the air stays in contact with the wing. So they're going to start here, and they're going to meet back on the other side. But they're going to meet back at the same time. So imagine you guys are leaving Mays High School. And you have to get to my room at the same time.
And cars.
One of you has to go up to 53rd
And go to Quick Trip.
and go to Quick Trip, not to mention any names, and somebody else goes straight to the school, right? Go with this. So who has to drive faster?
The one that goes to Quick Trip.
Vitor
One that
does.
goes to Quick Trip. Why?
Because it takes longer.
Why?
Because it's
a
more.
longer distance.
No, it doesn't take longer.
Oh, it's a longer distance.
There's a stop.
It's longer distance.
Nice.
Okay, there's a greater distance, so to get there at the same time, you have to go
Faster.
So as that air is traveling faster over the top of the wing, what's it creating?
A low
High
pressure
pressure or low pressure?
Low pressure.
Creating low pressure. So you're creating a low pressure system on the top of the wing. You have a high pressure system on the,
Bottom.
Bottom.
what are you going to do?
Create lift.
You're going to create uplift.
Wow.
So, why do they go and meet at the same time? Why does
Because
that
of this whole concept of laminar flow. Because the particle, because of the fact that once you split it, it still wants to end up back here. Where you run into trouble is when you
Together.
lose laminar flow, where you create pockets of turbulence. That's where bad things happen.
is that turbulence?
Yes,
Okay.
on that backside. So if you lose that laminar flow, where you get into like a flat spin or something like that, where you're not moving enough air over the top of the wing. And this is also a function of density. So like Vegas, for example, if you've ever flown out of Vegas, like on hot days, they will only, sometimes what happens is that the air gets so hot and it loses density, so the air is less dense, that you cannot create enough uplift because the air is so low dense that it won't create enough lift to get the planes off the ground. So that's why in Vegas, sometimes in the heat of the afternoon, they'll shut down the airport because the air is such a low density. Now, how you can use this.
Looking back around airplanes. Can we go?
So, but why the water in the pipe?
So think of pressure as the amount of collisions, not
Hold on.
because we think it's
Stop that camera for a second. I gotta find something. Okay, so I'm gonna take this ping pong ball,
molecules actually.
and if I just hold it up there and let go, what's gonna happen?
It's gonna fall.
It's gonna fall. Why?
Because there's gravity and there's no
Gravity's
suction.
pulling it down, right?
Yeah.
So what I'm gonna do is I'm gonna blow down through the top of the tube.
Nah, dude,
Okay? What?
don't tell me it stays.
I know. All I'm asking you is, so I'm gonna do this. Okay? I'm gonna go
Stop ruining the movie.
like this. Blow hard through here. I put the ping pong ball here.
Okay.
So it's only one of two options. It's either gonna stay
You're gonna feel like
It's
an
gonna
idiot.
stay.
or it's gonna fall.
It's gonna
It's gonna
stay.
fall.
But I'm gonna be blowing down.
I don't care.
It's gotta
staying.
stay.
The air's
It's
gonna move
gotta-
around it.
There's
catch
no
it up.
point you doing this if it doesn't
We've
stay.
been lied to too much.
That hurts.
I have trust issues
Have
with
I-
you, with
have
you,
I
Mr.
ever-
Bergkamp.
I've never blatantly. Okay, the whole gravity thing is a bullshit lie. But beyond that, everything else is still true.
What about
Gravity's not
Back
real.
up, back up, back
Okay, so now let's see what happens, right? Oh, that.
Yeah.
Oh, yes!
Why don't you blow, then put it there?
Hold on.
Told you.
What is even that?
That is crap. That's like
That's
when you
crap?
that's like when you get a roll of tape and you get
That
the
one.
thing and you spin it and
What?
you get an air pressure you get an air pressure hose
Yeah.
and you get a roll of tape and you blow it over the top and it stays.
Okay. So here's the
That
story.
sucks.
So if I let go of it, so is
Sucks.
gravity
Really?
still pulling it down?
Yes.
Okay? But when I blow through it, what do you know about the air as it's moving around it?
It sticks to it.
It's holding it
Creating a
up.
Well, it's moving fast.
Laminar flow. It's in
Flow.
contact with the ping pong.
And as it moves faster, what's it going to do?
Stay in contact for longer.
Yes. So the faster it goes, you create low pressure. So that low pressure
You're not blowing hard enough.
is lifting it up because you have the same number of collisions on the bottom, right?
Yeah.
But you have a smaller number of collisions on the top. You're creating a low pressure system. So it isn't being sucked up, it's actually being pushed up. So it's being pushed up by the collisions on the bottom because you have an imbalance on the number of collisions. So me doing this is the exact same thing that happened with the paper. Now, if it's not going fast enough, that was cool, right?
I'm so excited.
But if I blow faster,
Ooh.
So why does high pressure push on like low pressure?
no. You have an imbalance. So on the bottom side, you have
Has to
the
even
normal
out.
number of collisions because of the atmosphere.
Yeah.
But you have a lower number of collisions on the top. So it's being pushed up because you have an imbalance of numbers of collisions. Now,
It's kind of like
one more time.
the pool.
So I'm going to hold this piece of paper like
push
this,
down really hard.
okay?
It caves in.
And I'm going to blow
That's
over the
low
top
pressure
of
and
it,
the high pressure's here, so
gonna
it's
straighten
caving.
okay?
That's
So I'm
what
going to
it's
blow over the top of it. So what are three things that could happen when I blow over the top of it?
Paper straightens out.
Option number one, the paper could lift up and straighten out.
Mm-hmm.
That's option number one. What's option number two?
It stays.
Just stays there and goes, not doing anything because I'm in static equilibrium. Option number three, the paper actually gets
Flies away.
bent down. Okay, so it could go down like this, right? It could lift up, or it could just stay the same.
One.
Yeah, it's got to lift up
Why?
because low pressure on the top means high pressure on the bottom, and it pushes and levels out.
Now, let's, I want to delve into one thing that you said there. When I blow over the top, is that creating higher pressure on the bottom?
No, it's
just the
it's just a
normal
normal.
pressure.
I'm just not changing, it's the same pressure right now as it is on the top of the
You're just
bottom.
decreasing the pressure on the top.
I'm decreasing the pressure on the top, so it isn't that it isn't like I'm creating higher pressure on the bottom. I'm just having lower pressure
On the top.
over the top. Okay, you ready?
Yeah.
I do that.
Same idea, right?
Yeah.
The exact same idea. As I blow that over the top, you have a smaller number of collisions on the top with the same number of
Collisions.
on the bottom, paper lifts up.
I used to do that all the time when I was younger.
You make it look like I'm like doing some weird magic.
You're doing voodoo.
Voodoo I do. Okay?
Nah, that ping pong ball was a little bit crazy though.
Okay.
I don't like that one.
Now, if you ever watch NASCAR,
Nasty.
okay? Non-athletic sport centered around rednecks. That's what NASCAR stands for.
That's vile.
They need
Wow.
never mind. I was like, they need good reflexes, but all they do is turn left.
Well, it's actually tough. You talk about pulling some G's, and it's physically tough.
You see that guy that rounded the corner on the
Yeah,
wall?
bad.
Yeah, and
He
one.
took the wall and rounded it and got qualified because of it. Like he
'Cause
rode
he-
the wall all the way around
Really?
at max speed
No way.
and qualified because of it.
Hey,
Did it because he did it in a big
Okay, now, let's look at what's going to happen. You have two, this is looking down on tops of the cars. Okay? You have two cars, high speeds going like this. Okay? What's going to happen to the pressure in between those two cars?
There's none.
It's gonna.
Well,
It's going to be lower.
it's going to be lower.
Yeah.
Why?
Because there's going to be, because the air that's being moved with the car is going to be on both sides, so there's no normal pressure on the
That's
side.
right. So what happens with NASCAR is when they do drive close together, it's just like what happens with this paper. Okay? You're creating a low pressure system in between the two cars because that air is moving really, really fast. So when you drive, when they do that, they have to be aware of the fact that it's just going to be like just like these pieces of paper. Okay? They're going to get pushed together because you're going to have a low pressure system in between those two cars. And that outside pressure, even though that air is still moving on the outside because they're moving, but that air on the inside is being forced through there. It's like a canyon. And as it moves through that canyon, that's going to create low pressure.
Is
Okay.
So that's the same for like when I drive next to a semi.
Yes.
That's why I'm getting pulled towards it.
Yes. Okay. Now, this sometimes works and sometimes it doesn't.
Sometimes.
We'll try it. You might have to kind of spin this over.
Spitballs.
That's why there's like little.
That
What's this?
and
He nails you in the forehead. That'd be. I can do some mean spitballs.
I've never done one of those.
Spitball?
No.
I used to shoot.
I make no guarantees on this.
I'd be at
Sometimes-
restaurants and just shoot them across the.
Bro, I see
Okay.
this ad on TikTok, bro.
Hey,
So obviously, if I blow straight onto the ping pong ball, okay, goes like you'd expect.
yeah.
So what I'm going to try and do is I'm going to try and blow the air just on one side of it. Okay?
So it's
Curve
been-
it.
One more try.
Give it a bend.
Lemon or.
Oh,
It kind of worked.
Nearly.
kind of worked.
But no, back.
So what you saw,
That touch.
You
No touch.
need like a.
but what you will notice is that when I begin to blow, that ball will begin to move in that direction. Okay? So
Your legs are in the way of the door.
Why is blocking it?
So, what's happening, even when I blow that air over here, that you'll notice that that begins to move, and it's the same idea. I'm creating a low pressure system, that's gonna pull that over, because that low pressure, you have the same number of collisions on this side, smaller number of collisions on this side. Then as soon as it gets sucked into that, boom, it goes. Now, this one's a little tougher to do. I don't know if I have the wind capacity to do this one. But, oh, come on.
I believe in you.
But it had that, even with that aluminum can, it had that same effect. Now, let me try one thing with that.
Ping pong ball.
Oh, come on, get over center. That kind of work. Sometimes if you do it just right, it will actually begin to like just roll like symmetrical. But here's the whole point.
Gonna get himself high.
The faster it goes, the lower the pressure.
Breathe out.
Okay.
But he's lightheaded.
A little bit like that, I'm not gonna lie. Okay.
Let me try this.
So here's what's, so what I'm gonna do, what do we have left? Couple things. So I'm gonna actually run off the answer key to this. Okay, these are problems out of the book that deal with like flow rates and pressures and this whole idea of the continuity equation. So I'm gonna write these up on the board. This is not due, okay? I'm gonna scan this, I'm gonna send this, or I'll just give you copies of this tomorrow, so that way you don't have to worry about printing it out. So tomorrow, I will give you copies of this. This is not due, this is what I'm giving you, but this stuff is gonna be on the final, so you've gotta know how to do it. So before I forget, let me go ahead and do this. So this is out of chapter 13.
It's kind of weird.
Ooh, can we do the cannon again?
Yeah, it's not set up though.
Cannon was fun.
We should make a potato
Ooh, you mean to
cannon.
tell me this isn't weird, bro?
Magic Man. Oh,
That's weird.
What is?
Low
Vitor's,
pressure.
Vitor's a magician.
It's like how the straw works.
Yeah,
Yeah,
it's like when you put your straw in a drink, you do that.
yeah,
and then-
that's cool.
And that's what I do.
The same concept. Okay. I'm just saying.
Stop being logical. It's annoying.
Shoot it. I'll shoot it.
No. You want to?
Yeah, I'll shoot it.
Wait, so are we done with like assignments for the semester then?
Yep.
Guillotine.
Get it.
Guillotine.
No,
Oh,
that's
yeah, you
bad
were
for you.
That's that bad for you.
Whoa.
You done with all physics?
No, it still goes to the final.
No, I'm gonna take the second semester of my senior year.
What?
Are you coming back?
Oh, that's
Yeah.
that's.
I'm
gonna
only
be-
going for a semester.
Why?
Okay.
Why not go to senior?
So, if you want to get a feel for these problems, like I said, by tomorrow I'll have this copied and ran off. But if you want to work these ahead of time, so you can kind of see, hey, do I know what's going on? Because it combines buoyancy, like the YouTube problems. Okay, there's some of the YouTube problems on here. There's like flow rates where you have to calculate how long it takes to fill up like a certain size container, knowing the flow rate of the stuff coming in, okay, which is going to be important if you're going to be like controlling engineer, you kind of know, you know
Is
that.
that kind of like the most complicated that it'll get, or
YouTube problems.
where you have to find the flow rate and then find out how much time it'll
Yeah,
take?
that's Well, the most complicated ones are probably the ones with Bernoulli's continuity equation, just because you have all those different variables that you have to account for.
Because I always mix up rho and P, the pressure.
But yeah, that's yeah.
understandable.
Okay. So, like I said,
Length and
I will
angular
give you
momentum.
those tomorrow. Now, let's talk about your final. So let's say that I'm going to give you a rocket.
Yeah. Just one rocket problem.
I like the rocket
The
problem.
entire, the most ungodly rocket problem you could ever think of.
No.
Oh,
Can you make the world spin? Prove the Earth is spinning. That's our final.
No.
Yep.
You have to travel to at least 4 different countries. I will pay for the flights.
No, you won't. They'll be free.
No, Maze will.
Maze will. What countries are we going to?
Jamaica.
Jamaica, lads.
Listen, you dog man.
Fog one.
Why would you want? Bumper tour.
Yeah, man.
Time to bring me my money. That's why he's leaving.
You're gonna piss them off.
Shot.
Oh, sorry.
Shot in the head.
Ah, yeah, it is. There it is.
Rough.
Final velocity of is that rho over time?
No.
That's force over
Momentum.
distance.
Sorry.
Momentum,
It's
bro.
a little confusing.
Density
There's a lot
versus
of
time
P's.
graph for the rocket.
We should have one problem that goes over momentum, pressure, power, and rho.
Speak for yourself.
Oh,
I have, on the review, I have one that goes A through O.
Yeah,
Might as well make it go to Z, like.
No. Okay.
No
Too
fun.
much work.
So now, keep in mind, most of your test is going to be multiple choice, okay? You're going to have some free response questions to work out. Most of the test is going to be multiple choice.
Are we on the Star Wars?
So let's say I gave you this problem. Here's a rocket.
But he sucks.
Force from the engines is 30 newtons. Mass of the rocket is 1.02 kilograms. The first thing we have to figure out is the acceleration of the rocket. So what are you going to do?
You're gonna
I'm going to take that tube away from you.
acceleration of the rocket F equals ma.
Just going to take 30 newtons and divide it by 1.02.
Yep.
and then
Good with that.
9.8.
Yep. Like 30 point. Oh.
No, because that's only the
The accelerator,
It's
the
not
net
net
acceleration of
force.
the rocket.
that's not the net force. That's the force upwards, and then you subtract the force
So
gravity.
who, since you're launching this rocket straight up from Earth,
Oh, that's not net.
Gravity
oh
mafia.
no, that's your applied force.
Gotta pay the gravity mafia.
Yeah, you got to pay off the gravity mafia. So how much do you have to pay off to the gravity mafia?
9.8 times 1.02.
Like 10 newtons.
Yeah, like 10 newtons. Okay, that's why I specifically chose 1.02 kilograms. So, but it's multiple choice, and I promise you, if you do this wrong, if you take 30 newtons and divide that by 1.02 kilograms, you're going to go, score! Physics is not tough. F equals ma. I got this, Burkett.
Aces.
No.
Like minus 30.
Yeah. Okay.
It'll take on double.
Unfortunately, I'm a jerk, and I know every mistake you will make, and if you make those mistakes, those answers are there. So I'm just telling you, okay? Because you're going to feel good about yourself. It's like, whoa, this is good, right? This is easy, man. So you do have an upward force of 30 newtons. I'll give you that,
Can't believe 330 miles per hour.
okay? But the downward force is going to be about,
10 newtons.
which leaves you a net force of
About 20 newtons.
about 20 newtons. Okay? Cool with that.
Yeah, me.
Now, what are you going to do with 20 newtons to
Divide
get
it
the
by the
acceleration?
math.
Divide by the mass.
So somebody take 20 newtons and divide that by 1.02 kilograms.
19.6 meters per second.
19.6 meters per second squared.
Yeah.
Okay? How does that fit in with your velocity time graph?
That's a slope.
Slope of your velocity time graph.
It is.
Okay? So, at the end of 10 seconds, if we have an acceleration of 19.6 meters per second squared, assuming that the rocket is starting from rest, at the end of 10 seconds it is going
196 meters
196
per
meters
second.
per second.
Yeah.
Go with that. So our velocity time graph is going to start at
0.
0. At the end of 10 seconds, we're going to be going about 200 meters per second. Okay? With an acceleration of 19.6 meters per second squared. Remember, does acceleration tell you how fast you're going
No.
or the rate at which your velocity changes?
Rate of change.
It's a rate function. What we're saying, so at the end of 1 second, how fast is the rocket moving? 19.6. And the 2 is going to be going about 20. Okay? Ballpark. Now, what would the momentum time graph look like?
P equals MV.
Linear
It's just
sloping
newtons.
line?
Equals M,
just
P
newtons.
equals MV.
Well, how about this? Let's back up for a second. Let's back up the rocket.
But the mass is
What's the initial momentum of the rocket?
0.
0.
0. Do we have enough information to calculate the final momentum of the rocket?
Yes.
Because momentum is
Velocity times
mass times velocity.
Well,
Now, if we assume that the mass of the rocket stays constant, which in reality it isn't, but let's make the math easy.
then yes, we know.
Okay? So somebody take 1.02 kilograms
It's 200.
and multiply that by 196 meters per second.
Gotta be 200.
200.
Exactly.
200 Newton seconds. Okay? So at the end of 10 seconds, it has a momentum of 200 Newton seconds. Go with this?
Very.
What does the slope of a momentum time graph give you?
Newton's force. Force net.
Force. Gives you net force. What's the slope of the line?
20 newtons.
20 Newton seconds.
So it's
Because,
Newton seconds?
newtons
No.
or
per
20 newtons.
Oh, okay.
Because if you take 200 Newton seconds and divide that by 10 seconds, you get
20 newtons.
20 newtons, which is your
Net force.
Good
force.
job, Jackson.
Okay?
Yay.
Go with this.
Yes.
What does the area underneath that graph give you?
Newton seconds times seconds. Newtons per second. Newtons times second squared.
Nothing.
Which
Gives you
is
Absolutely
kV
nothing.
meters, which is nothing.
Okay? It absolutely, it's like talking to
I
a
was
friend.
getting there.
You really
It has no
Well, just
meaning.
making
Newton
sure.
seconds squared.
Because you get Newton second squared. What's
Help us.
measured in Newton second squared?
Everything.
My dreams.
Area.
Angular momentum.
My dreams. L.
Oh,
Big
L. L.
L.
L
It's an
minus-
L graph.
Louis
That's an
taking,
L
Louis
graph
taking
right
the
there.
That's
L
what
for the
radians
team.
is. That's what radians is.
Louis taking the L for the
Newton
team.
seconds squared is Bluetooth.
Now, at the end of this time, I shut off the rocket engines. So this is like me throwing this ball up in the air.
No way.
So as soon as it leaves my hand, what's the only force acting on it? Gravity. So what becomes the slope of my velocity time graph?
Negative
9.8.
9.8.
Negative 9.8.
Negative 9.8 meters per second squared.
Yeah.
So when you change the slope of a velocity time graph, what are you changing?
The acceleration.
And what do you have to do to change the acceleration?
Change the force.
You have to change.
Hey, do you
This
want the
baseball-
review?
And this distance, I could sever your head.
You want the review?
Wham! Sorry, Clemson, lost one of your soccer players. What happened? He said decelerated in physical class. Okay, that's valid. Okay. So, slope of this line
I had
becomes
to. I had to.
negative 9.8 meters per second squared. True?
Yes.
Okay. Where is it at its maximum height? At the top of that or that point?
That.
The top.
No, that one. That one.
Oh yeah, at the
This
zero because
Yeah.
it changes.
Why?
Because
sign.
it's changing sign, so that's where it
That's
goes to zero.
Is the slope changing sign
No.
or is
No.
the velocity
Velocity
changing sign?
changes sign.
Velocity changes sign. Okay? So we got that going for us. So when I shut off the rocket engines, what's going to be the slope of my momentum time graph?
Whoa. Negative 9.8, whatever it is.
No.
Wait.
Well, it's forced gravity, so it's whatever we
It
got.
wouldn't
for
be
that.
forced gravity. The slope would be forced
Negative
gravity.
10 newtons.
That, yeah. That.
Yeah,
That.
That,
Yeah.
yeah, that
that,
one.
What he said.
negative 10 newtons.
Let me sit by him.
Okay?
Test.
Because I shut off the rocket engines, guess what? That's my net force, which is going to create an acceleration of negative 9.8 meters per second squared. What would
The fox.
the force distance graph look like?
The force distance graph would just.
Force times distance is
It
work.
would just be the
That's-
same thing.
That's work.
It'd be a sloping line.
Wait.
Well, no, it would go up and then it kind of does it down again.
It would be the
No, it
it would be the same net force. It would be 20. It'd be the net force, right?
No, it would. Wait,
It'd be
is that
constant.
net force or applied force?
It's net force.
So it'd
Okay,
be,
so
it'd
just
be
be
20,
constant, drop,
and then it go to
constant.
negative 10.
Instantly. As soon as the rocket turned off. Or like very quickly.
20 newtons?
Yeah.
Yeah.
What does the area underneath a force distance graph give you?
Work.
Work.
Now, work also equals a whole bunch of different things. Fundamentally, it equals a change in energy, right?
Yeah.
True?
Yeah.
Yeah.
So we could change kinetic energy. We could change
Potential energy.
rotational. We could change UG. We could change us, right?
Yeah.
Okay. Which of
be
these
ice.
could we
This
calculate
is hard.
at this point? UG, KT, do we have to worry about us?
No.
No.
No, we don't have to worry about us.
Wait, how do you calculate KT? Or KR,
I don't
sorry,
know.
KR.
Yeah, we don't have to worry about KR.
Oh,
because
okay, I
the
think
rock-
so.
That's what I'm saying. It's
Gotcha.
not
Yeah, yeah.
spinning.
Barbecue roll.
Okay.
Barbecue roll.
Do we have
no.
enough? Could we calculate kinetic energy
It's
using
ungodly.
1/2 mv squared?
Yes.
Yes. Why not?
We could find the kinetic energy once it gets shut off. True?
Yes.
So somebody take 1/2 times 1.02 kilograms times 196 meters per second
Squared.
squared.
It's about
It's 200. No. It's
How would it even be 200? There's a 1/2 over there.
100.
There you go. There you go.
What'd you get?
19,500.
Pretty close.
So a little scientific notation.
1.966 times 10 to the 4th.
1.96 times 10 to the 4th joules.
200.
Which if you round is 200.
Pretty much.
Close.
Yeah,
It's 200 to the second.
whatever. So how does this fit with that graph? That's the area, right? That's the area. Because that's how much the kinetic energy changed.
Yeah.
Now, at this point, we shut off the engines. What does this graph do?
Sharply drop.
Then it goes down to negative 10.
Oh.
Now what's going to happen to the kinetic energy?
It's going to be negative.
Or the change, no. Is the kinetic energy going to turn negative?
No.
Energy's always positive.
Is the change in kinetic energy going to turn negative?
Yes.
Yes. Because I'm going to go from a positive kinetic energy to
A negative
a
connection.
negative value. Okay. So that's going to be a negative value. Is the gravitational potential energy going to continue to increase after I shut off the engines?
Yeah.
decrease. Oh, after. Oh, as soon as you
KT
I
or
shut off
UG?
the engines. Will my UG continue to increase?
Yes.
Why?
Because it'll keep going up.
Because it's going to keep going
Still
up.
positive velocity.
Positive velocity. Now, when I shut off the engines, which is analogous to me throwing this baseball up in the air,
Ball.
okay? Throw this up in the air.
Problem.
Does it continue to go up in the air because there is a positive force continuing to push it up that's
No.
continuously getting smaller?
No.
No.
Why does it continue to go up?
There's still positive
Because
net force.
the rate of change in velocity is negative.
Wait, no.
No.
It's because there hasn't
It's one word.
it hasn't
No.
slowed down.
inertia.
Inertia. Does the ball have inertia?
Yes.
Yes.
I thought we weren't allowed to use that word, to be honest.
Inertia?
Yeah.
What have you been
What
using?
word?
You literally thought it was L.
How many times have I used this word?
You literally
inertia?
thought it was L.
Have I ever said, oh no, you can't talk about inertia?
It's illegal.
It's illegal.
That's
Okay?
ever since.
Now, speaking of inertia,
It's not diesel.
Catch.
I got Hank and I got Bobby. Bobby the baseball and Hank, right?
Okay.
Okay? I drop both of them. True?
Yes.
I drop both of them. Which one will accelerate faster?
Neither.
Bobby or Hank?
Same.
Why?
Because G is constant.
Mass cancels out.
What one equation explains why they both have the exact same acceleration.
F equals.
Nope,
D equals V naught.
nope,
G equals 9.8 meters
Nope.
per second squared.
close. That's close.
FG equals MG.
Big G
Oh.
M over R
Oh, yeah,
squared.
that.
Ew.
That, one of the most important equations in all of physics.
Just get
This
rid of
little
that.
gem right here. What does that M represent?
Massive.
Mass of the Earth.
Mass of the
Earth.
Earth. Is that the mass of Hank or Bobby?
No.
No.
Bobby.
What's R?
The radius of the Earth.
Radius of the Earth. How far you are from the center of the Earth. This is one of the most fundamental equations that exists in all of physics, because this explains why Hank and Bobby all accelerate at the same rate. Because that little value G is not dependent upon the mass of what's falling. Now, is there more force acting on Hank?
Yes.
Yes. Why?
'Cause
Or
he's had
mass.
More
And
mass.
More
F
mass.
equals
There's
M.
more stuff, right?
Yeah.
Lots
Now,
of
because Hank has more stuff, Hank has more
Inertia.
inertia. Okay?
chaos.
So when I drop them, now the tendency you would think is like, man, this thing's heavy, right? Heavy. So in the Aristotelian view of the world, Hank should fall faster because there's more force acting on it. Seems reasonable, right? Seems reasonable.
It's
More
got more
force,
inertia.
yeah, should accelerate faster.
It'll hurt.
But Hank also has more stuff. And so because Hank has more stuff,
Hank needs more force.
Hank needs more force to get to the same
Destination.
acceleration. Right? Got that.
Yeah.
One of the things I might ask you to do is calculate, I might give you information like on the moon, okay, and ask you to calculate little g. If this was a multiple choice question, and it's multiple choice, keep this in mind, it's multiple choice. First off, what units does that M have to be in?
Kilograms.
Radius has to be in meters. What are the odds that I give you both units in kilograms and meters?
Really slow.
Absolutely zero.
Yeah.
Okay? Absolutely zero.
Never really.
But if you use those incorrectly, what are the odds that that answer is there?
Most likely.
100%.
Like, yeah.
Now, this is multiple choice.
Just
We get the
cruel.
mass of the
Just
moving grams.
Maybe ounces.
What?
Maybe what?
Maybe glazed donuts.
Glazed donuts. There you go. You got to do the conversion from glazed, not chocolate covered donuts, glazed donuts.
Long
Completely
John.
different densities of the
Long
frosting.
Johns.
Long Johns are the super
Now-
weird
Long
donut.
John.
Graham crackers. Kilogram crackers.
Okay.
Now I think we're all just hungry. Like, I-
Now, if it's multiple choice and you know you could potentially do this calculation wrong, what does your answer have to be less than?
9.8 for the love of
9.8 meters per second squared. So if I give you this problem, guess what?
Less than 9.8.
Eliminate the ones that are
Well, okay,
more than 9.8 meters
If you
per second
already
squared.
know the, is it gonna be exactly the thing?
That's what I was
with the
gonna
moon?
ask. Would
Because-
you lie to it? Like, would you put like, depending on
What do you
the?
mean what I like? Again,
Yes,
this is,
all the
I'm just
time.
saying. I'm just saying.
Again,
all the time.
I'm hurt twice today. You have accused me of lying.
I mean, like,
I mean, bold-faced lies.
Because it's 1.67.
yeah,
right?
that's what I was gonna say. It's 1.67. You wouldn't put something like the actual answer to be something else,
Yeah,
right?
just go for it.
if we,
It is your favorite, so.
I did-
Moon gravity. You can dunk.
that's your
I used to be able to dunk in Earth gravity.
that's your favorite gravity,
Used to be
remember?
able
You
to.
used to be able to dunk?
No, Earth is the
Those
He's
so
6'3",
much.
you think he couldn't dunk?
Hey, I know a lot of 6'3" people that can
That
dunk.
is valid. That is valid. Back in
Justin
the day.
Stevens struggles.
So, again, just look at it.
They got
I mean,
props.
I'm just telling you, just think it through. Okay. So let me explain what I'm gonna give. I'll go ahead and give you all this stuff today, even though the test is on Monday, if you want a head start.
I want to add
Yeah.
Justin
So,
Stevens.
you're gonna get,
Connor, you need a head start, man.
Wow.
you're gonna get 4 pieces of paper, okay? So let me explain the function of each one. So, the first one is gonna be big topics that are gonna be on the final, okay? Now, buoyancy, that type of thing, okay? Gas laws, isometric, isobaric, isothermic, okay? When does delta U equal 0? When is Q positive? When is Q negative? Okay? That's pretty much going to play out like probably the multiple choice portion of it. Okay? I'm worried about the planetary motion stuff just because you have the potential to make
A lot of mistakes.
a lot of mistakes.
Yeah.
Okay? So, if you remember, let's say something's orbiting near Earth orbit around the Earth or around the Moon. What's your order of magnitude for orbital period in seconds or velocity in meters per second?
10 to the third.
10 to the third. Again, it's multiple choice. You don't see something that's 10 to the third, guess what?
Cross it out.
Probably not going to happen. Okay? So, that's what this is.
What if it's a weedy
Okay.
weedy big?
Then, this one is problems all the way from the beginning of time up to here.
Adam and Eve.
And it ends with like a cube of styrofoam, cube of iron, both fully submerged in water, explain the differences, similarities, and all the forces acting on the cubes. Okay?
Coops.
So that comes with this answer key here. So this consists of 36 questions. This is a separate thing. So this is everything from the beginning of time up to here.
Good work.
Okay? Beginning of time up to here. Now, the other one that you're going to get, this is just thermodynamics and isobaric, isovolumetric, buoyancy, that type of thing. And so this is just 9 questions. But question number 2 goes A all the way through O. Okay, literally. It's like, oh, it's just one question. Well, it goes A through O. Okay? So I'm going to go ahead and hand these out. We're going to spend more time tomorrow working through problems, okay? But if you want to get a head start on that review,
So
you
it's
have this available.
it's Monday paper test, Tuesday, Wednesday lab test.
Exactly.
Good job.
I need to use the bathroom.
Wait.
What?
I have a question.
Can I just, my book's
How are we gonna get over here if we have
How what?
on when?
Just come.
What do you
Just
do?
skip your class, bro.
No, but I have a final in there.
Tell them.
What do you mean? Tell
Tell them you're not. AP Physics is more important than your dumb class. That's
them.
what
A push.
Tell Mr. Kerr that.
Are you planning on dropping out already or what?
Kill me.
Your class is stupid.
I know.
Is that third block?
But we test Monday and Wednesday, and it's like the whole.
You mean all of next week? Yeah.
Yeah.
What do we do?
Let me get
What do you
the.
mean?
Don't you have?
Maze High doesn't have the same schedule as us.
Yeah. So then what do we do?
You just come here.
Instead of.
Hey, push.
You're staying?
Are we gonna get a question,
I'm
like,
confused.
it's a rocket? Because I was like doing some review questions, and it's like the rocket goes up, it comes down, except it has like a crosswind.
No,
No? Okay.
I'm having
I won't throw crossword.
crosswords.
I had to,
Thank you for that.
because I have a friend.
Will you give us equations or no? Like
If there's really something weird, I'll give it.
like planetary motion though, or
If
no?
there's something weird like that, I'll give it to you.
What about
Giving us
I?
all the moment of inertia equations.
You will have them.
Yeah.
What about F equals ma?